In the last video, we saw that if we had some curve in the xy plane, and we just parameterized it in a very general sense like this, we could generate another parameterization that essentially is the same curve but goes in the opposite direction. It starts here and it goes here as t goes from a to b, as opposed to the first parameterization. We started with t equal a over here, and it went up like that. And the question I want to answer in this video is how a line integral of a scalar field over this curve, so this is my scalar field, it's a function of x and y, how a line integral over a scalar field over this curve relates to a line integral of that same scalar field over the reverse curve, over the curve going in the other direction. So the question is, does it even matter whether we move in this direction or that direction when we're taking the line integral of a scalar field? And in the next video, we'll talk about whether it matters on a vector field. And let's see if we can get a little intuition to our answer before we even prove our answer. So let me draw a little diagram here. Actually, let me do it a little bit lower because I think I'm going to need a little bit more real estate. So let me draw the y-axis. That is the x-axis. Let me draw the vertical axis just like that. That is z. Let me draw a scalar field here. So I'll just draw it as some surface. I'll draw part of it. That is my scalar field. That is f of xy right there. For any point on the xy plane, we can associate a height that defines this surface, this scalar field. And let me put a curve down there. So let's say that this is the curve C. This is the curve C, just like that. And the way we define it first, we start over here and we move in that direction. That was our curve C. And we know from several videos ago that the way to visualize what this line integral means is we're essentially trying to figure out the area of a curtain that has this curve as its base, and then its ceiling is defined by this surface, by the scalar field. So we're literally just trying to find the area of this curvy piece of paper or wall or whatever you want to view it. That's what this thing is. Now, if we take the same integral, but we take the reverse curve, instead of going in that direction, we're now going in the opposite direction. We're now taking a curve where we're going from the top to the bottom. But the idea is still the same. I don't know which one's C, which one's minus C. I could have defined this one as, I could have defined this path going from that way as C, and then the minus C path would have started here and gone back up. So it seems in either case, no matter what I'm doing, I'm going to try to figure out the area of this curved piece of paper. So my intuition tells me that either of these are going to give me the answer, the area of this curved piece of paper. So maybe they should be equal to each other. I haven't proved anything very rigorously yet, but it seems that they should be equal to each other, right? In this case, let's say I'm taking let me just make it very clear. I'm taking a ds, a little change in distance. Let me do it in a different color. A little change in distance. And I'm multiplying it by the height. And I'm multiplying it by the height to find kind of a differential of the area. And then I'm going to add a bunch of these together to get the whole area. Here I'm doing the same thing. I'm taking a little ds. And remember, the ds is always going to be positive, the way we've parameterized it. It's the hardest word in the English language for me to say. So here, too, we're taking a ds, and we're going to multiply it by the height. So once again, we should take the area. And I want to actually differentiate that relative to when you take a normal integral, and you take a normal integral from a to b of, let's say, f of x dx. We know that when we switch the boundaries of the integration, that it makes the integral negative. That equals the negative of the integral from b to a of f of x dx. And the reason why this is the case is if you imagine this is a, this is b, that is my f of x. When you do it this way, your dx's are always going to be positive. When you go in that direction, your dx's are always going to be positive, right? Each increment, the right boundary is going to be higher than the left boundary, so your dx's are positive. In this situation, your dx's are negative. The heights are always going to be the same. They're always going to be f of x, but here your change in x is a negative change in x when you go from b to a, and that's why you get a negative integral. In either case here, our path changes, but our ds's are going to be positive. And the way I've drawn the surface, it's above the xy plane. The f of xy is also going to be positive. So that also kind of gives the same intuition that this should be the exact same area. But let's prove it to ourselves. So let's start off with our first parameterization, just like we did in the last video, we have x is equal to x of t, y is equal to y of t, and we're dealing with this from t goes from a to b. And we know we're going to need the derivatives of these, so let me write that down right now. We can write dx dt is equal to x prime of t, and dy dt, let me write that a little bit neater. dy dt is equal to y prime of t. This is nothing groundbreaking I've done so far, but we know the integral over c of f of xy, f is a scalar field, not a vector field, ds is equal to the integral from t is equal to a to t is equal to b of f of x of t, y of t, times the square root of dx dt squared, which is the same thing as x prime of t squared, x prime of t squared, plus dy dt squared, which is the same thing as y prime of t squared, plus y prime of t squared, all that under the radical, times dt. This integral is exactly that, given this parameterization. I have so much trouble saying that. Now, let's do the minus c version. I'll do that in this orange color. So the minus c version, actually let me do the minus c version down here. The minus c version, we have x is equal to, you remember this actually just from up here, this was from the last video. X is equal to a plus b minus t. X is equal to a plus b minus t. Y is, sorry, x doesn't equal a plus b minus t. X is equal to x of a plus b minus t. Got ahead of myself. X is equal to x of a plus b minus t. Y is equal to y of a plus b minus t. And then t goes from a to b. T goes from a to b. And this is just exactly what we did in that last video. X is equal to x of a plus b minus t. Y is equal to y of a plus b minus t. Same curve, just going in a different direction as t increases from a to b. But let's get the derivatives. So I'll do it in the derivative color maybe. So dx dt for this path, it's going to be a little different. We have to do the chain rule now. Derivative of the inside with respect to t, well, these are constants. Minus t, derivative of minus t with respect to t is minus 1. So it's minus 1 times the derivative of the outside with respect to the inside. Well, that's just x prime of a plus b minus t. Or we could rewrite this as this is just minus x prime of a plus b minus t. dy dt, same logic. Derivative of the inside is minus 1 with respect to t, right? Derivative of minus t is just minus 1, times the derivative of the outside with respect to the inside. So y prime of a plus b minus t, same thing as minus y prime a plus b minus t. So given all of that, what is this integral going to be equal to? The integral of minus c of the scalar field f of xy ds. What is this going to be equal to? Well, it's going to be the integral from, you could almost pattern match it, t is equal to a to t is equal to b, of f of x. But now x is no longer x of t. X now equals x of a plus b minus t. X of a plus b minus t. It's a little bit hairy, but I don't think anything here is groundbreaking. Hopefully it's not too confusing. And once again, y is no longer y of t. Y is y of a plus b minus t. Y of a plus b minus t. And then times the square root, I'll just switch colors, times the square root of dx dt squared. What's dx dt squared? Dx dt squared is just this thing squared, or this thing squared. This thing, if I have minus anything squared, that's the same thing as the anything squared, right? This is equal to minus x prime of a plus b minus t squared, which is the same thing as just x prime of a plus b minus t squared, right? You lose that minus information when you square it. So that's going to be equal to x prime of a plus b minus t squared, the whole result function, square it, plus dy dt squared. By the same logic, that's going to be, you lose the negative when you square it, y prime of a plus b minus t squared. Extend the radical, and then all of that dt. All of that dt. So that's the surface integral over the regular curve C. This is the not the surface, the line integral. We're not doing surface integrals yet. This is the line integral over the curve C. This is the line integral over the curve minus C. They don't look equal just yet. This looks a lot more convoluted than that one does. So let's see if we can simplify it a little bit. And we can simplify it perhaps by making a substitution. Let me get a nice substitution color. Let's let u equal to a plus b minus t. So first we're going to have to figure out the boundaries of our integral. Well, actually, let's just figure out what's du. So du dt, the derivative of u with respect to t is just going to be equal to minus 1. Or we could say that du, if we multiply both sides by the differential dt, is equal to minus dt. And let's figure out our boundaries of integration. When t is equal to a, what is u is equal? U is equal to a plus b minus a, which is equal to b. And then when t is equal to b, u is equal to a plus b minus b, which is equal to a. So if we do the substitution on this crazy hairy looking integral, I should simplify a little bit, and it changes our. So this integral is going to be the same thing as the integral from u. When t is a, u is b. When t is b, u is a. And f of x of this thing right here is just u. X of u. So it's simplified it a good bit. And y of this thing right here is just u. Y of u times the square root times the square. Let me do it in the same color. So times the square root of x prime of u squared plus y prime of u squared. Y prime of u squared. Instead of a dt, we have to write or we could write, if we multiply both sides of this by minus, we have dt is equal to minus du. So instead of a dt, we have to put a minus du here. So this is times minus du. Or just so we don't think this is a subtraction, let's just put that negative sign out here in the front, just like that. So we're going from b to a of this thing, right, like that. And just to make the boundaries of integration make a little bit more sense, because we know that a is less than b, let's swap them. And I said at the beginning of this video, if you swap for just a standard, regular, run-of-the-mill integral, if you have something going from b to a of f of x dx, or du, and maybe I should write it this way, f of u du, this is equal to the minus of the integral from a to b of f of u du. And we did that by the logic that I graphed up here, that here, when you switch the order, your du's will become the negatives of each other when you actually visualize it, when you're actually finding the area under the curve. So let's do that. Let's swap the boundaries of integration right here. And if we do that, that'll negate this negative or make it a positive. So this is going to be equal to the integral from a to b. I'm dropping the negative sign because I swapped these two things. So I'm going to take the negative of a negative, which is a positive, of f of x of u, y of u, times the square root of x prime of u squared, x prime of u squared, plus y prime of u squared du. Now remember, everything we just did with the substitution, this is equal to, just to remember what we're doing, this was the integral of the minus curve of our scalar field f of xy ds. Now, how does this compare to when we take the regular curve? How does this compare to that? Let me copy and paste it to see. No, I'm using the wrong tool. Let me copy and paste it to see how they compare. Let me copy, and then let me paste it down here. Edit, paste. So how do these two things compare? Let's take a close look. Well, they actually look pretty similar, right? Over here for the minus curve, we have a bunch of u's. Over here for the positive curve, we have a bunch of t's, but they're in the exact same places. These integrals are the exact same integrals. If you make a u substitution here, if you just make the substitution u is equal to t, this thing is going to be the integral from a to b of what's going to be this exact same thing of f of x of u, y of u, times the square root, well, I'll put another parenthesis, square root of x prime of u squared plus y prime of u squared du. These two things are identical. So we did all this substitution, everything, but we got the exact same integrals. So hopefully that satisfies you that it doesn't matter what direction we go on the curve. As long as the shape of the curve is the same. Doesn't matter if we go forward or backward on the curve, we're going to get the same answer. And I think that meets our intuition because in either case, we're finding the area of this curtain.